Good morning everybody and welcome to our webinar. Today's webinar topic is challenge in how to transfer technology from R&D to production. My name is Stefan Ringbeck and I'm product manager here in Trina. The webinar will take approximately 20 minutes. After this we will have a short question session, so Q&A. The Q&A we will do it for 5 to 10 minutes, so the total time should be 30 minutes. If you have questions, then please write it in the question or in the chat, and after the presentation I will go to the chat and the question pane and will check for questions. Today the webinar will for sure be recorded and will be distributed after the webinar in the coming days. Today I want to show you a little bit about the status and for sure the challenges of the transfer. What are the challenges to transfer technology from the R&D lab to the production line. Then I will give you an outlook on coming technologies, so what can be expected, and then at the end a short conclusion. Why we speak about this? The status is, as you know, we have the levelized cost of energy and there's a certain breakdown. And here on the sheet, on this slide, I want to show you the impact on the different categories of the cost breakdown. The cost breakdown has a balance of system part, it's a BOS part, separated in a fixed part, for example inverters, in a variable part, for example substructure cabling, the module, and though the green marked area is the system, the system design and the components. Then we have on the other side DEV for development, project development, though typical for utility scale projects. Then we have OPEX. OPEX is operation maintenance cost. And then financing. Financing is the financing of the project, as I said, especially for utility scale. And you can see other direct and indirect impacts. For example, the system design for sure gives direct impact on the green marked area, on the system, because it's components, the component costs, and the finance. The financing is impacted by the bankability. For example, Trina here in the Bloomberg research placed at number 1 in this most bankable module you can have or you find in the market. And then we have also an indirect impact on the operation maintenance. Why indirect of the system design? If you select the components, you decide for a certain quality level. With the quality level, you impacting your operation maintenance costs as well with the system design. For example, do you have a tracked system where you have to check the gears, the motors, or you have a fixed system, an east-west system? For example, how easy it is to clean, can you go through the power plant with a machine for cleaning? And for sure the component quality, so how often do you have to exchange modules, how often you have to exchange inverters, how often do you have to exchange, for example, combiner boxes, and how the complete power plant is performing. So does the inverter perform on the expected efficiency? Does the module work on the expected efficiency, and what is the degradation of the different components? Now I want to show you although a short outlook of what is expected in terms of L3 in South and Central Europe. You can see here currently the LCE is expected between 5 and 8 cents, and this should be reduced in the next, let's say now 9 or 8 years. Until 2025 it's expected to be between slightly below 4 and slightly above 6 cents. As we already know, if you look on the Middle East, there are projects already ongoing with an LCE of $2.5–3 but they also have a higher irradiation. And this leads also to the question, why is it difficult? Because as you could see, one of the major drivers is cost down, and also the cost down has to be transferred from the R&D lab to the production line. That means increasing the efficiencies can lead to additional costs, and this process needs to be done in an efficient way to not have a high cost increase with higher efficient modules. Here you can see an overview about what is state of the art, where we are placed, and what can be achieved with different kind of technologies. So you can see here typical In the R&D labs, for example in Fraunhofer, there are cells with different junctions, or for example heterojunctions or triple, quadro, or even more. There you can achieve 46%. With standard products, so products in mass production, that's here marked with the red box. There the efficiency is between, as you can see here in the zoom, between 21 and 25%. And with the major technologies, so if you look on the crystalline one, it's around 20, 22. For sure, if you have, for example, IBC cells, then you're higher, but for mass production like polycrystalline and standard monocrystalline, it's around these values. If you now take a look on the cost of the module, on the left-hand side, you see the cost breakdown of a typical multicrystalline module in 2014. You see the cost for the silicium, for the ink-hot casting, for the wafer costs, on the cell costs, so transferring the wafer to the final cells, and then the module cost, what is typical, the assembling, the frame, the foils, junction box, and this kind of stuff. So you can see that the major part is the cell, and the minor part, so roughly 40%, is everything else beside the cells. On the right hand side you see a projection for the cost, and though it can be expected that, for example, the crystalline can or will be around 34 cents or even below in 2020. And you also can see that, for example, the learning curves for the different kind of technologies are different. The highest capacity, production capacities we have are for crystalline technologies. So for example, for CIGS, what is a thin film technology, the learning curve is lower because they also have a lower volume in what they produce, and they also have a different kind of technologies what has different challenges to bring efficiency to mass production. The same is for cadmium telluride. Now I want to show you a little bit about what is the possible roadmap to, or the known roadmap to higher efficient cells. You can see here that we are coming from simple junctions and we have selective emitter. Then we go for sure with monocrystalline one with additional technology, for example PERC or Pearl. Then we have passivated contacts, tandem cells. Tandem cells, for example, are well known already from thin film industry. For example, thin film silicon had already tandem cells with an amorphous microcrystalline cell. This can be also brought on the crystalline world, for example, that you have an amorphous silicon layer on top of the crystalline wafer, what is known as, for example, HIT. Then the IBC cell with some passivated backside, and then tandem cells with IBC, though the combination of different technologies. Now I want to show you the different challenges and the challenges behind. What I already mentioned in the beginning, the challenge what we have to face as solar industry is to compete with other energy sources. That means to be attractive for our customers, we need to achieve different kind of grid parities. As you know, there are different kind of levels. The first one is for households. Here on the right side you see a split or the cost for different countries, mainly in Europe, with different costs in the household. And you can see that prices for electricity, especially in the households, are quite high. And as we know, in most countries, even in northern European countries, the grid parity with household electricity is already done. If you now take a look here on the graph, on the left side in the graph, in the diagram for industrial, you see that the cost for industrial electricity is quite different from country to country, and usually much lower than for households. On the left side you can see an extrapolation or an assumption what is expected to be achieved when. So here we had the electricity grid or the electricity price with roughly 10 cents with a slight increase, and then different LCU development in Italy, the South Italy, and in Germany. And you can see also in Germany that we expect to be in 2016 at industrial grid parity, but for sure this depends also on the branch. If you have a branch with an extremely high energy demand, then for sure they will buy in the energy on a very low level. And for sure, at least we have the utility level, so competing with conventional power plants, so like nuclear, coal, or gas-fired, though the big ones, which have usually even much lower LCE costs. For sure, the cost is only the production and doesn't covering the grid, but it's the same for utility one, who also has the cost for the producing the energy, and then on top you have the cost of the grid. Because basically you can use the same feed-in point if the other plant is not existing or out of order and you're building a renewable one directly beside the old power plant. Now I want to show you the example where we already achieved. Here you can see in Essenry in Ireland we are quite good. Though with the south-facing system we already did it with east-west, it's on a similar level. In Stockholm, due to the extremely low electricity costs, we are above the industrial level, but we already achieved the household level. Though for industrial there is still some space to go, but the future and the upcoming technologies will show the direction, and as we also see the price decrease says also that we will achieve it in a few years. If we go now for Sandur, what is in Turkey, there we are far below the electricity cost for consumer for industrial electricity. That's a very good sign, though that makes sense to go to the customers and say, hey, if you invest into PV, if you want to have, and if you have direct consumption, though you can utilize your roof and reduce your energy bill, that's a clear benefit for a customer because you can produce the electricity for more like 5 cents and or around 5 cents, but if you consume it from the grid you pay 13 cents. And also in France we are below. Though what is the challenge? The challenge for sure, if you look on the left side, you see there the different kind of development states. If you're looking on the first part, that is the early development, you have the extremely fast increase, and you're fast in development, you achieve high efficiency or a certain efficiency in a very short time. But as you can see, we are on more like on the end, though we are on the flat part. Though the developing becomes harder. That means the process needs to be more clean. You have higher requirement on the equipment. The deposition process needs to be more homogeneous on the surface. That means you need a higher and better quality control. You need a better understanding of the processes, and this makes it more hard to achieve because if you want to control processes more accurate, you usually have to invest more into machinery, or you have to change some machineries and you have to develop new machineries where you are able to achieve a higher level of cleanness on the cell, so during the process, or a higher level of homogeneity during the process. And this is one of the challenges why it sometimes takes more time to transfer technologies from R&D lab to line, because it's also different if I do it in a lab where I have more time, or if I do the same or want to achieve the same efficiency level in a production line where everything is counting the seconds, because the seconds you need every every minute you need more for the product means additional costs, which is leading to higher product costs. And as we could see, to achieve the targets, to achieve lower levelized cost of energy, we also have to reduce the cost in the fab. That means shortening the times and optimizing the processes. As I showed before, we are quite confident to reduce the prices. They're also depending on the learning curves and the different tools, and as we know, there are new technologies and new machineries upcoming with short processing time and stuff like this, where we are able to further reduce the costs. And also due to the expansion of the production capacity, a certain reduction is expected. Though what's coming next? Though, as you can see here in the graph, we have the multicrystalline with approximately 20%, then the monocrystalline, what is also good introduced in the market, well known, and there we know the efficiency although the high efficiency, and also the LCOE is proven. Next, for example, can be monocrystalline with PERT, with a high efficiency, with less light-induced degradation, and with, for example, bifacial products. But the question mark is also around the LCOE. Designed, for example, with heterojunction technologies in monocrystalline one, also then with IBC cells. IBC cells especially due to the production costs. So we know the aesthetics, so for example for residential products the aesthetics is very high. The risk of LID is extremely low, but due to the high production cost, the LCOE is a question mark. So there further improvements are required to be in the wide market successful. So currently it's more niche, a product for niche applications. So for example, if you want to have the highest energy output out of your roof. And then for example N-type, though there are more and more question mark, and also the silicium-based tandem products, where we see, okay, more like everything, so how is the R&D lab, what can be done, and how can be these processes transferred in a cost-efficient way on mass production. And also the stability, so the long-term behavior, because as we know, most of the power plants are planned to use for at least 20, 25, 30 years, and though the product needs to be stable to also have low operation and maintenance costs. Though what is the current state at Trino Solar? Though we are coming from the base multi-crystalline one, then in current production is the honey technology in multi and monocrystalline one. Honey means basically a textured cell. Then we have the honey plus. The plus is for PERC, and with the structured cell. And what's coming next, what is in the pilot phase, is IBC. But for sure we're also taking a look for the IBC how we can reduce the cost to get out a very attractive product. What is future? Here you can see at one solution can be heterojunction, then for sure the IBC cell, what is currently in pilot, then heterojunction combined with IBC, and then the tandem cells. The basically cells consist of several layers of different absorbers to have a better spectral response. That means spectral response means always how much of the sunlight, though the different sun colors, you can collect, and if you can collect more, then you also have higher efficiencies. So the spectral response, that means the collecting of the sunlight of the different colors, of the different wavelengths, is very important to achieve higher efficiencies. Now, as last slide, a short conclusion. Now if I go back to the beginning of the presentation where I have the different cost figures. As you can see, it's exactly the same graph with breakdown, and it shows the different impacts, and although with a question mark. So if we take now a look on the green part, improving the efficiency, it has a direct impact for sure on the module. It has a direct impact on the balance of system on the variable cost. So if you have a high efficient module, you need less cables, you need less substructure. But it also has an impact on operation maintenance. So product stability like degradation, let's say sensitivity, for example, or does breakage rate increase, or I don't know. But there are several points to check to have a reliable product. So for sure the target is also to have more reliable products, so to extending the warranty, to have less issues in the field, to have lower degradation, which leads to lower number of modules you have to exchange, and this brings down the operation maintenance costs, and this is a clear benefit because it's a reduction in the LCOE and a higher profit for your customers. And also financing, because if you have lower capex or the lower investment costs, then you also have slightly lower financing costs. Lowering the costs for sure has, in this case, so if you have the same efficiency but lowering the cost, then the impact is basically on the module. The indirect impact is on operation maintenance. So can the lowering cost be achieved with the same quality standards, or do you have to make a compromise? And also on the financing. Though, for example, if you have, there are different kind of players in the market, tier 1, 2, and 3, and may you have selected a very cheap product from a tier 2 or 3 player where you don't know the quality of the product, and then yes, you have lowered the cost because the module you bought it in or you procured it for low amount of money, though you paid less. But then later for the financing, maybe you have to invest more because the product is not so bankable. Or later, after a few years, so let's say after 5 or 10 years where you can see the issues, you may have to exchange because the quality wasn't as expected and you have trouble and you have an increased exchange rate, what leads to high maintenance cost, and the project gets less beneficial for your customer because he has a lot of maintenance costs and what are reducing his profit. I want to say thank you already for the time. I will now check for questions and answer the questions. Though one of the questions is, what is the usual industrial time or time to market for innovation in PV? This depends a little bit on the step, though this can go quite fast. Let's see, from several months, but can also take 1.5, 2 years. But this clearly depends on the technology and how much you have to change. So if you have a minor improvement, like for example you optimize the process, for example for deposition or for cell treatment, so cell processing, then you can do it within several months because you only have to play with the settings in the machinery. But if you want to implement a complete new technology, then you may have to exchange machines, and then it's more in direction half a year, 1.5 years. That's a question regarding the cost. Though yes, the graph I showed is from someone at beginning of the year or last 2015. Though at the moment there's a quite fast decrease. So there's also an acceleration in the learning curve. But if you check, for example, for other learning curves, I mean, it should only show in which direction it can go and can go faster. For example, if you can procure the material on a cheaper level, it should show the direction. And if you look for other graphs for the learning curves, it shows always that you have a certain phase where you have a faster decreasing of the price, and then you have a time where the price is more like constant, and then you have another step. And the steps are currently not shown, though it's a pure linear decrease of the price. There's a question regarding this, regarding thin film technologies, and if they will become competitive. As I understood the question, there I would say it depends on the technology. For example, if you take a look on cadmium, or if you take a look on cadmium tellurides on first law, I have to say they do a good job, and they also catch up in terms of efficiency. But if you take, for example, a look on CIGS, they are not so fast in gaining efficiency, especially under the cost pressure what is in the market. Though it depends a little bit on the technologies if they are able to catch up. but I would say it will be an interesting game to see in the future what are or what is the behavior of the different technologies and who can develop and who can go the race. There's a question if you can have tandem cells by simply adding some steps in the fabrication or during production. The basically should be possible, but what we don't have to forget, it depends also on the. It's not only adding the processes, so adding layers. It means also maybe different processing of the fab, not of the fab, of the cell, before adding additional processes. So if you add additional processes, then maybe you have to process the cell before differently. And though it's hard to say if it's that only adding steps or if it also leads to changes in the early beginning of the production line. But this for sure will be identified by our R&D team and how to do and what is the easiest way to achieve higher efficiencies with tandem products to get them stable and also to have them on a good cost level. There's a question about bifacial solutions. And there we have to say yes, we think about bifacial solution products in the future. But there we will have likely then a more detailed webinar in the future. So I guess there is now time for, let's say, one or two more questions. Then I will close the session. We will take a look on the questions, on the remaining questions after the webinar, and then distribute them later in a short Q&A session. There's a question about the cost difference between mono and multi, and will be mono PERC mainstream product in 2017-18. I would say the share of PERC products will increase, especially for residential, and depending on the market or on the country, it will also have a certain share in projects. The cost difference, or let's say the price difference, it's better to say, it's usually quite small. For PERC for sure it's a little bit higher than for only the difference between multi and mono. But at the end it's not only the module, it depends on the complete system. So how much you can save on the balance of systems side to have, for example, a more beneficial project. So you have to take a look on the module, the technology you use. So let's say a multicrystalline, monocrystalline, or mono with PERC technology, and then you can take a look on the complete system and decide on the system cost, what is the best solution out of it. So should I go for a little bit more expensive module and then saving on the balance of system, or should I go for, let's say, a multicrystalline, or for cheaper solution and then adding more substructure, more combiner boxes? But this also depends if you have the space for it. There's a question, though this I will take as a last question for the talk. There's a question why is there different, or why different learning curves for different technologies. I mean, if you take a look on the market, the main market or the main products in the market are crystalline based, and for example for cadmium telluride there is only a few companies, so mainly First Solar, who is doing cadmium telluride, and then you have also different kind of volumes. So if you take a look on the volumes of what is produced on a crystalline substrate, there it's much easier because you have more experience, and as you know, experience is based as well on how much components, how much products you have produced, because every product is gaining experience. And also in the R&D lab, if you have you have much more R&D labs based on the companies who are producing crystalline technologies for crystalline cells than for thin film cells. And so this is also a reflection of the shares within the market. And for sure, if you have a high volume product, then it's easier to reduce the cost compared to a product or to a technology with a lower share in the market. Now I want to thank you again. So thank you for your attention. If you have further questions, then please write me an email. Well, my email address is stefan.ringbeck@trinasolar.com. After the webinar, we will place the recording and the presentation online, and we will also distribute it to you. Thank you very much. Have a nice day and enjoy the holiday season. So enjoy your Christmas time, the time off, and Happy New Year. Thank you very much. Goodbye.